Welcome to Circuit Valley. I'm Gaurav, continuing my series of decoding protocols and buses on using an oscilloscope. I'll be publishing a new video today, and this video is going to be unique. I do not think there is much public information available about this bus or how it looks on an oscilloscope and how can you decode it and make sense out of it. So we're going to take a look today this really special bus from automotive domain called FlexRay, and we're going to generate some flex rays. I really do not have any usage for this. This appears to be one of the top of the line buses from the automotive domain, even though more and more companies are moving towards Ethernet even in automotive, but still FlexRay and CAN and LIN, these protocols are still used. And we're going to take a look today at FlexRay, and we are going to generate FlexRay from a demonstrator hardware. I do not have really good usage of FlexRay in my lab, so I do not have any application of it. We are going to generate FlexRay from a hardware, and we're going to take a look at its data. To show you the bus setup, my oscilloscope is connected to the flex output from this demonstration. This PCB is really special. It can generate all the protocols you can imagine. If you want to know more about this particular board, you can watch my first video in this series and you will get what is this board capable of. We will take a look at my MSO 804A. How does it decodes it? The only oscilloscope which I have is capable of decoding FlexRay is MSO 804A, my RTP2004, and my Tectonics cannot decode it. So we are going to take a look using this big oscilloscope that how does this bus looks. Right now on your screen you can see there is a FlexRay packet available. There is quite a bit undershoot and overshoot because I do not have proper termination on this bus, but for our oscilloscope it doesn't matter. We can still decode it without a problem. Let's separate the signals so that you can see better. I'll do a signal capture, and this is how the bus looks. It appears to be idling at a middle level, around voltage level around 1.8 volt or something like that. And you see there's a positive and negative and differential bus similar to CAN, but this bus is more capable than CAN. Can go up to I think 10 megabit per second and stuff like that, so it can do a lot more than that. And let's go and set up a trigger first. I do not understand how do you set up a trigger for stuff like this, but maybe we can set up a trigger on this pulse. Let's measure it. Okay, something like this. So we'll set up around 8.2 microseconds. Let it run. So we'll take channel number 3, sorry. Pulse, positive going pulse, and it should be greater than, I will just do greater than 7 microseconds, and we will set up a threshold appropriately. Let it run. Is it triggering? No, it's not triggering all that much. Setup channel number 3. Time is greater than 7 microseconds. Positive going pulse. I think I measured it wrong. Maybe delta is different. So delta is 8 microseconds. That is correct. We'll reduce it to 6 microseconds. Now we see a somewhat stable trigger. Okay, and I think there may be some spurious pulses right here in the middle where the cursor is, so it doesn't matter. We have found one trigger to ourselves, and bus is now more stable. We are going to set up a decode. Data is constantly changing because as per the specification of this board must be sending data at 10 megabit per second, and swing is going to be 0 to 3.3 volt, and there are 15 individual 198 bit long frames. So we will take a look. Let's remove the markers so they're taking up the screen. Protocol setup for FlexRay. So channel A or channel B, we are measuring both, and data source channel number 1. Let's see if it detects. No, it doesn't detect. Maybe channel number 3. Yeah, so stuff like that. There's sometime incomplete packet, so you will see sometime red marking there. Okay, so we'll do a single capture and we will see if we have detected this 198-bit long frame. And packet is 128-bit, 128-bit. I do not see any 198-bit frame. So they all appears to be 128-bit frames. Let's look at the memory itself. How much memory? 1 megapoint memory we have. Okay, so there are some frames, null frames, every kind of frame available. I do not really understand. I can't even debug if something is not right or something is wrong. Maybe they are talking about 198-bit of total frame length. And there must be 15 frames. I think our flex bus generally ends right here. If you want, I can show you what are the triggers available for the flex protocol, for FlexRay, cycle TSS, any TSS. I do not know what does it mean. Let's let it run and we'll find out. Okay, so let it run. Is it triggering stably? I would say it triggers somewhat stably. Automatically we didn't do. Okay, sync frame, normal frame. I do not really understand FlexBus or FlexRay. I do not really understand FlexRay, so cannot tell you what is right, what is wrong. But it's just to show you a demonstration that this also exists. And you know one more thing. So this is a series of video. This was the 8th part, and till now we have decoded SPI, I2C, UART, CAN, LIN. We have also decoded a parallel bus. We have decoded I2S, and we have also decoded MIL 1535. So till now these were all slow speed buses. Now we'll go to the high speed buses. For example, USB HS, and I'll also decode USB FS and LS. And we will also go to MIPI. MIPI is primarily used in displays and everything else. And then we will go to Ethernet and we will see what we can do there. That's it for this video. You can visit my website www.circuitwell.com.